Thanks very much for the invitation. So before I start, I should say this is a joint work with Carlson, Ribeiro, and Segara. So let me define what a network is for me before I start. So a dissimilarity network is a pair x omega x, where this is a finite set, and omega x is a function from x cross x into real numbers, such that the function vanishes on the diagonal, and only on the diagonal. So in particular, I don't want to impose symmetry and no other conditions like triangle inequality. So just one first example of the sort of things I have in mind. So if you take alpha and beta, you can consider the following two-node network, which we represent in this way. And the assumption here is that, well, the omega of PQ is alpha, and the omega of QP is beta. And I'll call that network delta 2 of alpha beta. It will be a player for some things that come next. So the general idea is that we imagine that we have, and this is what motivates the work. We have networks, and networks are difficult to understand, difficult to represent, and we want to simplify networks and somehow project them onto an easier space via some map that retains some essential features. So we want to compute some, say, invariants of networks, and we hope the invariants are easy to visualize and they are interesting and informative. And so we imagine there's some sort of a simplification or sketching going on, and this is some space of invariants, also called features, which are easy to interpret. And here interpret means easy to visualize, at least. So actually the only example that I'm going to talk about is the case when I is a collection of all possible dendrograms. So dendrograms look like this. So you would take a network and you would produce something that looks like a rooted tree, and which is a function, say, from the positive reals into the partitions of x. And you can obtain a partition of x by slicing that function. I mean, this is a diagram with a certain value of t. So let me say precisely what I mean by a dendrogram. A dendrogram over the set x is any function theta x from 0 infinity into partitions of x, such that at 0 you have the partition of x into singletons. Then for some sufficiently large value of t, the partition you get is a partition of x into only one component. So there exists a t0 such that theta x of t0 is the one block partition. So here we have all the different elements of x as the leaves in this tree. And at the beginning, you start with a singular partition. Sufficiently late enough, you will get a partition into one block. But you also want to say that as you increase the parameter t, you get coarser and coarser partitions. So this is a so-called hierarchy condition. So for all s greater than t, theta x of s is coarser than theta x of t. So we want then to take one of these objects and obtain some meaningful dendrograms. And I will frequently just also keep the set. It's informative. It's useful to keep the set x over which the dendrogram is defined. And D will be the collection of all dendrograms. So let's see one first family of examples. So it tends to happen that in the applied domain, people know many methods that are defined on symmetric networks. So say that I take n and I impose symmetry here in this definition, and then I obtain n sim. And there are many possible methods that people know that attach a dendrogram to a symmetric network. For example, the so-called single linkage, average linkage, complete linkage. So there are many choices here. So it's natural to think, I mean, do I have some good ways of symmetrizing and then applying a method? And in that way, I would have induced some possible ways of analyzing asymmetric networks. So a natural choice here is to say that this symmetrization map that goes from n into n sim, you take x, omega x, you map it into x, and what you do is you transpose the function and you take the max element wisely. So that's one possible map. And in that way, you can induce one method. Some methods, if you make some choices for this method h. So let me recall one of them, the so-called single linkage method.
Network. Okay. What is n here?
N is a collection of all networks.
Okay. What is n sim?
N sim is a collection of all networks which are symmetric.
What does that mean?
Symmetric means that
Omega y is
exactly. So let's say x, omega x, is symmetric if omega x of x, x prime, is equal to omega x of x prime, x. And I'm looking at some maps that take a network, possibly asymmetric, and symmetrize it. And one possible choice is a zeta map that simply takes the element-wise maximum. If you think of omega as a matrix, omega and omega transpose. With that choice of a map, then you can try to identify some candidate here for a method that simplifies symmetric networks, and you can compose. So let me recall the so-called single linkage map that goes from n symmetric into dendrograms. So the way it operates is the following. You take x. Let's say that you map that to theta x, single linkage, and you declare that theta x, the partition that is necessary to define at some value of the parameter t, is equal to x modulo the following equivalent the equivalent relation that I call sim t, where I say that x is sim t equivalent to x prime, if you can find some sequence of points starting at x and ending at x prime, such that omega x of xi plus 1 is bounded by t for all I. Okay, this is a definition for symmetric networks. So what it means is that you have your data, and these two are t equivalent if you can walk from one to the other so that the consecutive jumps are all bounded by t. Now, I'm trying to produce maps from here to here. So I'm going to take this composition and let me record what is a induced notion of clustering that appears here. So since I'm symmetrizing first and then applying this equivalence relation, you're going to be saying that 2 points x and x prime are equivalent if you can go forward, say t equivalent, if you can go forward and backward through a chain of points so that you don't jump more than t. Right, because I'm composing the symmetrization with the single linkage. So let me call this, for future reference, U for upper x prime. And the induced method will be HU, this method here. So that's one construction. That's something you can do. So you're symmetrizing and then hoping for the best. So let's see another example. Can I write here? Is it okay?
Can you explain that picture? If you go in less than t in two vertices, that picture?
Yes,
That?
sure.
What's that?
What I mean is that I'm taking a possibly asymmetric network, that pair, then I symmetrize it, and I obtain, say, this omega x bar, which is this one here. And then to that one, I'm applying single linkage. So single linkage means that for me to be able to walk from, say, to join x and x prime and put them into the same equivalence class for some parameter t, I have to be able to walk, to choose a sequence of points so that two consecutive jumps, that the jump between two consecutive points is bounded by t.
But what does that mean, bounded by t? How are you going to measure it?
That because you have this inequality. This is inequality that defines the what I mean when I say bounded by t.
Can't you do that without even bothering to symmetrize?
Yes. That gives rise to other methods as well. But this is one that people use frequently in practice. Okay. When you take into account that you have already symmetrized, the picture that arises is this one, because this is the effect on the original network, which is asymmetric. So that's why I draw it like this. You have some consecutive little jumps in two directions. The other construction that is natural is the following. So let's call it HL for lower. So the U before was for upper, and that will become clear in a second why I choose those different names. And what I'll do here is I'll say I map this into x theta x super L, And I define theta x super L at t as x modulo some equivalence relation. And the equivalence relation is the following. So I say that x is TL equivalent to x prime if I can find a sequence starting at x, x1, so that somewhere along the sequence I find for some xk the point x prime, then I continue and I go back to x0. So, and then the condition that I require is that all consecutive jumps are bounded by t. So pictorially, what this means is that you start at x, you have x prime, and you have found sequence of points so that all these jumps are bounded by t. So you have a loop spanning the 2 points, and all consecutive jumps are bounded by t. So that defines another method, HL. So one observation is that the partitions that you produce by HL are always coarser than those produced by HU, because you have more freedom for joining things. So I will denote that by saying that HL is bounded by HU. So another remark is that when you constrain yourself to symmetric networks, HL and HU obviously agree. But in general, they are different. So one can generalize this construction. Actually, one can give rise to a family of methods that interpolates between these two methods. And let me show you how one would be able to do that. So say intermediate methods. So if you have any x, a finite set, consider for some k at least 2 integer and some t, the relation R super k t, given by saying that you can find a sequence of k points such that all the jumps are bounded by t. So that gives me a relation. Then I take, so it's asymmetric. Sorry, it's not symmetric. So yeah, this is correct. So then take the transitive closure of RKT and call that wiggle KT. So now that will interpolate between the two relations that you already find. If you take k to infinity, I mean a very large k, then you obtain that behavior. You're allowing yourself to take very large loops and to come back. But for k equals to 2, 0, 1, and 2, you start at x, you go to some point x prime, and then you come back. So for k equals to 2, you obtain the relation that I called sim upper of T. Okay? So that's a generalization. And let's write it here. It's going to take me a couple of minutes to draw it. So each of these has at most k elements in the loop, and you start at x and you end at x prime. So let's call that method hk. And the observation is that h2 is equal to hu, and formally h infinity is hl. So very quickly, we gave rise to quite a few constructions, and there are many more actually that one can come up with. So it's probably interesting or useful to try to understand which constructions are meaningful, or at the very least healthy. So
is there anything you've done so far that requires you to start with a finite set?
no. It's just that that's, say, the status quo. I mean, people always work with finite sets. The data is finite, so we analyze that type of, say, data sets. I mean, potentially you could write the theory with infinite sets, but I'm not sure.
I mean, I'm just thinking, if I have an underlying space, and I mean, this asymmetric relation, right? It can come from, it doesn't have to necessarily be a distance. Like it would be a dynamical system, right?
Yeah.
That's carrying points around, right? So I could use this to kind of, obtain things like chain recurrent sets and things like that.
That would be quite
There
interesting.
are lots of actions on the space that you could reinterpret as this omega.
No, I agree.
You could think of trying to
Would be quite interesting to think about something like that. Yeah. Say our understanding is in this simpler setting, the finite one. So can we say classify methods h from n into d? I mean, how can one try to order the methods and try to say this is a better method, that's a method that doesn't behave so nicely? So the idea here is to try to view methods as transformations that respect some sort of underlying structure. So let me explain what I mean. So suppose that you have a method h, and you look at the output of your method when applied to a given data set, and then you get some dendrogram. Then you apply your method to another data set. You get the corresponding output. But suppose that you know that there's some relationship between your inputs. And there's some map phi that tells you how structure here is represented here. So then you would like to say that your method is somehow respecting this mapping of structures. So, of course, the underlying idea here is to understand n and d as categories and h as a functor. So then idea make n and d into categories and demand that h be functorial. choice we make for making n into a category is, well, the objects are just the dissimilarity networks, but we say that morphisms in n between two networks are all the set maps such that the weights omega x don't increase under the map. And we also make D into a category where the objects are just dendrograms and the morphisms are again set maps such that for all t, theta x of t is finer than the pullback of theta y of t. So if you demand that h be functorial from n into d, so that means that intuitively decreasing weight makes it easier to cluster. Right? That's the obvious conclusion of the, or the direct conclusion of these definitions. So now, these are three methods that I showed as examples. The three of them are functorial. So something that happens is that all the HKs for K at least 2 are functorial. Something besides that is true, something else. So there's a theorem here that says, suppose that H is any functor with the property that when you convert, when you simplify this network delta 2 alpha beta, what you obtain is the following dendrogram. So here you have one of the points, that's the other point, but then you demand that the scale at which they merge is the maximum between alpha and beta. Now then, H will be bounded between H infinity and H2. So the examples that we constructed are actually extremal in some sense. So this doesn't answer the complete question. I mean, I'm not yet able to enumerate them all. I'm not able to classify the different methods. So it's interesting to put forward more properties that allow to pin down at least some subfamilies. one property that seems to be natural when analyzing real data, I mean, is that you don't want your method or the results that you obtain by applying your method depend on the units that you used. So one possible additional property that we may impose is scale preservation. So let's say that H, some clustering factor, is scale preserving if for all functions C from R plus into R plus with so that they preserve the 0 and they don't vanish anywhere else and increasing. The following is true. Well, let's write it here. So what we want is that when we apply C to a given network, we obtain the same as applying C to the dendrogram. So let's see what this means. So C from n into n, that's clear. So you just send x omega x into x C of omega x. That will be an element of the space of all networks. But now, if you want to apply C to dendrograms, well, you send x theta x.
How does that composition make sense?
I'm explaining what composition means. Yeah. So by that I mean I have to explain how to apply C to either elements in the space of networks or dendrograms. So the action of C on dendrograms is the following. So you take a dendrogram and you send that to x theta x composed with the inverse. So for example, requiring this means that if you say scale up all distances, then you have to come back to the origin in the original dendrogram because it became more difficult to cluster. So that's one additional condition. And let me give a small variant of this. In general, we call this scale preserving, but if C is linear, then we say linearly scale preserving. So it's important then to try to identify methods that satisfy this property in addition to the other properties. Now, there are a couple more properties that I wanted to mention. So let me choose where to write. So let's consider the following idea. So suppose that you take a network data set and you apply some method h, and you obtain a dendrogram. So you look at the dendrogram, and then you say, all right, I'm going to slice the dendrogram with some value of t. That gives you a partition. So in particular, you have access to blocks. So take one of the blocks. So what happens here is that you have the partition theta x of t, and then you're choosing a certain block b in the partition. Now you say, well, this block is a subset of x. So I can conceive of creating a subnetwork, b, omega sub b, where omega sub b is just the restriction of omega x to b cross b. And then you can think, OK, what happens if I apply my method again? So we say that h is excessive if, when you apply h again to omega b, you get b and then theta x restricted to b. So the idea is that excessive methods are methods that are locally consistent. So let me write this. Intuitively, excessive methods implement the idea of local consistency. Now, I'm not going to give the construction right now, but there's a remark I want to make. There exist non-excessive functorial methods. So these sort of things do happen in practice. I mean, you could write some methods that are not tame. And another idea that we found useful is related to, say, complexity. OK, I think it's already used. So
what's the smallest number of elements that you get for a non-excessive functorial method?
Minimal number of elements of what?
Yeah, can you find a finite set X with a non-excessive
So that the smallest construction that we have is, I think, 4 points, if I remember correctly.
4 points?
Yeah. So, OK, so let's rewind a little bit. So I wanted to provide some new conditions that one may be able to impose on methods to further winnow, say, to thin out the space of all possible methods, as given by this theorem we had. So the first one was some sort of a scale invariance. Scale invariance is very natural. You just don't want your method to depend on the units that are given your data. Then I talked about excessiveness. So intuitively, you want some sort of a local consistency. And the third intuition here is some sort of a complexity of methods. And by complexity, well, I mean this complexity in the sense of how easy it is to describe a method. Do I have to give a finite list of objects that parameterize a method? Should the list be infinite? Or would such a list not exist at all? That sort of thing. So that leads to the idea of representable methods. So before, I was motivating some methods that arise in the following way. You have the collection of all possibly asymmetric networks. Then you symmetrize them somehow. And then you apply some natural candidate here to obtain a dendrogram. So it turns out, and this is something that follows from the theorem, that remember that any method that is functorial and satisfies the condition that it agrees with something predefined on the set of all possible two-node networks is bounded up and down by this HL and HU. That came from the theorem. But we also observed that HL and HU agree on M symmetric. So therefore, the theorem implies uniqueness of the method you could choose here. There's a unique method, and that method is what I called before single linkage. So let me now call it H asterisk. You have only one choice for such a method. So now, then this means that in this sort of picture, when I try to factor through symmetric networks, the richness has to come from what I do here, from these symmetrization functors. So representable hierarchical classing methods are methods that you can write as H is equal to applying single linkage composed with some map lambda. But those maps are special. Yeah, it's the first part of the definition. I will, yeah. It's a long-winded definition, so I wanted to give the intuition first. So we say that H is representable if H can be factored as single linkage composed with some functor lambda from n to n sim such that, and now things become, I need a little bit of patience from you, but so let me write the output first. So such that there exists a family Q of some special networks So N1, these are so-called generalized networks, or also motifs. So here, Q is a finite set, and omega sub Q is such that the domain may not be the whole of Q times Q. For example, before I give a formal definition, but this could be one of these motifs. Right, so I don't have weights in the opposite directions, but this is allowed in one of the generalized networks. But you still have that the weight function vanishes at the vertices. When you repeat, you get a 0. Okay, so that's the only difference with original networks. You let the domain perhaps be smaller than the whole q times q. Now, if you have a q motif and some x standard network and a map phi from q into x, the expansion constant of phi is just the maximum of overall q's and q prime in the domain of omega q, different of omega q of q, q prime, and up here you have omega x of phi of q, phi of q prime. So you're just looking at how much you're distorting the weights by embedding into x. And I will eventually go back to the definition that I have to give. All right, so what I have to do right now is to define this lambda x. Lambda x is a function from x cross x into the real line, into the positive reals. So then, if you fix x and x prime in x, I define lambda x of x prime as the infimum of this expansion constant over all phi from q into x, such that x and x prime are in the image of phi. So here's a picture. So we have x, and you have x and x prime. And here you have your q, and you have a map. And you want your map to have x and x prime in the image. But then you look by how much do I have to expand or modify things so that I find the map phi. Make sense? Or?
I mean, if I just think about that as your own omega is a matrix, right?
Yes.
Zeros on the diagonal. If you give me the q, you've given me entries in there.
Mm-hmm.
So why can't I just embed that? What am I missing? I mean, I just take a bigger matrix, right? Where I just put in number. I mean, that's
X is a data set. This is the one that you're trying to symmetrize. And I give you one motif, something that I say, this is an important structural element in your data. It may or may not be realized in your data, but it's something that I think is important for your analysis. Then you're trying to map this one down into X in such a way that your two chosen points are in the image of a certain map. But you want to do so by the following way. You want to scale this one up enough so that you find a weight non-increasing map from this one into that one down there. So let me see if I can say some. Okay, let's do an example. So suppose that my Q is exactly this network. 2 points, P and Q, well, Q and Q prime, and then the weights are 1 and 1, like the delta Q of QQ. So what I'm trying to do is to, and suppose that here you have X, and that's capital X, and that's X prime, and the weight here is alpha, and that one is beta. So now I'm looking for maps from here into that one, so that x and x prime are in the image. And then I'm asking, how much do I have to scale this one up so that I find the distance as a weight non-increasing map down into here. So that value will be the maximum between alpha and beta. Which, by the way, proves that this is the map that you obtain, the symmetrization factor arises by this choice is the same as the zeta that we had before, because it's the maximum of the omega x prime, omega x prime x. Yeah. All right, so coming back to here, we have this definition of the lambda x. And this lambda x depends on Q, your chosen motif. But if you have a family of motifs, like I said before, I allow some family of motifs. So then you take an infimum for Qs in your family. And that's the number that appears here. OK, so that one will depend on this family Q. All right, so we then have a definition of what it means for a method to be representable. A method H is representable if it factors through symmetric networks, meaning that I have a symmetrization factor that can be parameterized by some choice of motifs. So that's what gives rise to this notion of complexity. If the collection of motifs is small, well, your method is easy to describe. If the cardinalities of all the motifs that intervene are also small, well, you can also argue that your method is easy to describe. But now the interesting feature of all this is that this all the notions that I mentioned up to now, the 3 additional notions, can be linked in a theorem. So let H be a clustering factor such that, as before, it has a prescribed behavior on networks with 2 nodes. So then H is representable if and only if H is excessive and linear scale invariant. So in a way, the methods that are easy to describe, low complexity methods are those that exhibit some sort of local consistency. Now, so I think the main question that we like right now is, well, we have, I think it would be interesting to try to see what happens here. I mean, how crazy is that world of non-excessive methods, which will be automatically non-representable? But there's some constructions there. I think we have infinitely many methods. There's a whole family of them. But we don't know if those are all the ones that there should be. So, thank you.